I want to talk with you today about data lakehouses. Data lakehouses are something that you read a lot about. You find that different vendors talk about them, and so I thought it would be kind of interesting to go through the evolution that our industry has gone through in order to get to the point of building and thinking about and working with data lakehouses. So with that in mind, I want to talk to you about something called the evolution of data architecture. As far as I can tell, there have been four major uh, aspects, four major steps to the architecture of data that we see today. In the beginning were applications. Then we moved to something called data warehouse. Then we moved into a newer version of data warehouse, something called DW 2.0. And today we're talking about building data lakehouses. So let's go through now. Now, some of these things you're probably very familiar with. Some of these things you may not be familiar with, but so let's go from the very beginning. How did all of this data architecture stuff start? In the beginning, we had simple applications. We had input, we had a computer, and we had output. And that was the world was a simple place back in those days. And that's what we thought we had to do to build computer systems. And it turns out that people started to like these applications, that there's a lot of reasons why automating things was a good idea. And the next thing you know was we started to have applications everywhere. And then one day somebody said, gee, I've got some data over here in one application and I'd like to use it in this other application. Can I do that? And an innocent looking little program called the extract program began to be something that we found everywhere. Now, extract programs were intellectually very simple to do. You read some data in one place, you find the data you're looking for, and you throw it somewhere else. And so, from a standpoint of simplicity, extract programs were something, pardon me, were something that looked to be very simple. It turns out that these extract programs had a very negative connotation to architecture, because with these extract programs, we turned into something that we can call spiderweb systems. Now, I happen to get this drawing. This is a real drawing. I'm not going to name the company that I got it from, although it's been years ago. And each one of these little black boxes in the background here represents an application. And the little colored lines represent the extract programs that this organization had. Now, just for your information, there were over 10,000 developers in this organization. So each one of these little boxes represented anywhere from 2 to 3 people to maybe 100 people. And so this is what developed when we started to use extract programs. Now, this was a large organization. This was not a small organization, but this is what developed. There's a word for these kind of systems, and that word is something called spider web systems. And so what's wrong with spider web systems? It turns out that there's a lot that's wrong with spider web systems. But the main thing that's wrong with spider web systems is the fact that there's no data integrity. If you can imagine yourself a manager in this organization and you have all this data, it's not a matter of saying, do I have data? It's a matter of saying, what data do I have is correct? Because the same element of data exists in God knows how many places, each with a different value. So if you're a manager at a corporation like this, trying to use all of these applications as a basis for understanding what's going on in your corporation, this was a nightmare. And so this is, now, by the way, there were other difficulties with spiderweb systems. Spiderweb systems weren't or the lack of integrity wasn't the only problem with spiderweb systems. There were other problems as well, but the main problem was that of the integrity of data. So this is the first phase of data architecture that existed in the world of applications. And where did the world of spiderweb systems lead us to? The world of spiderweb systems led us into something called a data warehouse. We needed a change of architecture for the data warehouse. And so what was or what is a data warehouse? By the way, I think it's really kind of interesting. The definition of a data warehouse was laid out, golly Moses, 25 or 30 years ago. And the definition of what a data warehouse is and was has not changed to this day. And I find that personally to be remarkable. So what is a data warehouse? A data warehouse is something that's subject-oriented, non-volatile, integrated, time-variant collection of data in support of management's decisions. That's what a data warehouse was, and it was an architectural solution to a technical problem. Another way of thinking of data warehousing was the data warehousing was a single version of the truth. It's a place that you can go into the organization and find out what information is correct. Now, the general architecture for looking at a data warehouse looks something like this. Over on the left-hand side, we have some applications. We have something called ETL, technology called extract, transform, and load technology that takes the application's data, loads it into a data warehouse. And how do we know how to make the transformation? We know how to make the transformation by means of a data model. The data model becomes the roadmap for understanding what data we have in the corporation. So from an architectural overview, a rendition, this is what the world of data warehouse in its simplicity. By the way, there's a lot more to this. I hope that when you get into the real world, you're going to understand that that there's a lot more to this than what I'm showing. I'm giving you the high-level overview today. Then we find out that ETL does something. When people think of loading the data warehouse, a lot of people think of we just copy data over from one application into the data warehouse. And that's not at all what's happening there. The people that think that don't understand what's going on, because there's a fundamental transformation of data that's taking place in the data warehouse. For example, over here on the left-hand side, we have applications, and this is a very simple example of something that's very complex. But one application has chosen to specify gender as M and F and distance in terms of feet. Another application has chosen to specify gender as male and female and distance in terms of inches. The third application has specified gender as being a 1 and a 0 and distance being in centimeters. Well, each of these applications has the right to name the data and treat the data as they wish. But when you go into the data warehouse, you need to have a singular understanding and treatment of the data. So we need to figure out some way to specify gender, and M and F is as good a way as I can think of as any. What that means is that the applications that have male and female and 1 and 0 need to convert the data, transform the data. Same thing for distance. We can choose centimeters as a way for specifying distance, and for those applications that have feet and inches, we need to make the transformation. So it's not a matter of copying data from an application. It's a matter of fundamentally transforming data as we go into the data warehouse. And this is something that that people just don't understand. People hate this process of transforming data. Why? Because it takes work and it takes using your brain in order to do that. And anytime in this world when you ask people to use their brain and to do work, you immediately get resistance. Another aspect of the data warehouse is the data warehouse becomes a very good place for storing historical data. You see, in these applications, we didn't store data very long, a month, a week, 24 hours. That was typical of what we would find for the length of time that data resided in the application. But we go to the data warehouse, and what we find is the data warehouse becomes a very good place to store lengthy amounts of data. 5 years worth of data, 10 years worth of data, and even longer than that. Now, one implication of this storage of data over time is that data warehouses grow large, that you're going to end up finding more data in your data warehouse than you had ever expected. Years ago, somebody said that the data warehousing was the full employment act for people building and making storage. And there's a truth to that. We found then that once we built our data warehouse, it becomes a good foundation for business intelligence. With the data warehouse, for the first time, you can look across the corporation and have vetted, consistent, pardon me, 1 second. That with the data warehouse, you can have a true foundation for doing business intelligence. And so that's the relationship of data warehousing to business intelligence. Then comes another stage in the development of our architecture. This is where we have something called DW 2.0, and you can think of DW 2.0 as this, that when you look at the data in the corporation, there's stuff called structured data and there's stuff called text. And when we look at most corporations today find that 95% of the decisions are being made from structured data. What is structured data? Structured data is where we have the same structure of data repeated over and over again. And you can think, for example, of a bank account activity where you put money in the bank or take money out of the bank. You can think of going down to Walmart and buying something at Walmart, and the record of what you bought, the day you bought it, is captured. And so is everybody else. Everybody that buys something from Walmart has another record created, and each of the records have the same structure. And so that's what we call structured data. Corporations and database management systems are designed for handling structured data. That's what they do well. That's what they do efficiently, and that's what we find. But we find that when you look across the corporation, quite frankly, most of the data in the corporation is not of the structured variety. Most of the data in the corporation is of the textual variety. And what do we do with text in the corporation today? We don't do much. That we can capture text, but we can't analyze it. Let me give you a quick example of what I mean by not being able to analyze text. I don't know if you've ever looked at medical records, but something called the EHR, Electronic Healthcare Record. If you look at EHR records, they are designed for one doctor and one patient. And that's good. Believe me, we need one doctor and one patient. That's good. What they're not designed for is looking at 10,000 patients at the same time. So if we're going to be doing medical research, we need to be able not to look at one patient. We need to be able to look at 10,000 or 100,000 patients at the same time. And so that's an example of the limitations of text. And why are electronic healthcare records the way they are. They're the way they are because they're written in the form of text. As long as EHR records are in the form of text, they're not going to suit the needs for doing medical research. So when we look at text, what do we find in text? We find a wealth of information that's being overlooked by the corporation today. We have voice of the customer. What are your customers saying about your company and your products? We have email. We have the internet. We have call centers, insurance claims, police reports, contracts, surveys, medical records. There is a whole wealth of textual information in your corporation that isn't being looked at today. And that's a shame. You know, the other day, somebody asked me, said, Bill, I'm a senior in college and I'm getting ready to go out into the working world. Where would you recommend that I go? And I'm going to tell you, I said, look, go into the world of textual analytics, because textual analytics is like the state of California in 1848. In 1848 in California, I've heard stories, I wasn't there, but I've heard stories in 1848 in California, you could walk along the streams of California and just pick up gold. And I believe those stories. I think they're right, because in 1849, the world discovered there was gold in California that could be picked up out of the streams. And so everybody started to go to California. Well, there's going to be a gold rush towards textual data because vendors, computer vendors, database management vendors don't have the capability of handling text. So if you're looking for opportunity in the world, go look in the internet, go look on email, go look in contracts. There are 100 different places to look for opportunity that nobody else is looking at today. Now, I don't know if you know it or not, but there does exist technology that allows you to go from text to a standard database. So is it possible to read text and put it into the form of a standard database? The answer is absolutely yes, it is possible. It's being done today, and it's really exciting technology. Once you're able to put text into the form of a database, there's several interesting types of analytics that you can do. You can do correlative analytics. You can do sentiment analysis. And there's other kinds of analysis you can do as well. But sentiment analysis, this is where you go look at the internet and find out what people are saying about products and services, and then tell corporations about that. Correlative analytics, this is where you can go into, say, medical records and answer such interesting questions as, gee, people have COVID. What are the correlative conditions to COVID? What about smoking? What about cancer? What about age? What about gender? What about you name it? And how do those factors relate to something like COVID? Now, how important is information about what relates to COVID? Let me tell you something. People are dying for that kind of information. I mean, it's truly life and death kind of information. So that's what can be done once once you put your text into the form of a database. So as an example of correlative analytics, you have correlative analytics for the manager, and you have a Pearson coefficient matrix, which is the correlative analytics for the technician. And in doing so, you're able to look across 10,000 patients and say, this is what is going on with the patient. So now let's go into the world of the data lakehouse. So, pardon me, one day somebody discovered that, gee, there's more data out there than textual data and more data out there than structured data. There's also something called machine-generated data. Now, what is machine-generated data? Let me give you a couple of examples of machine-generated data. Years ago, I worked at a steel mill in Bethlehem, Pennsylvania, and as the steel is poured into they call them heats, and when they create a heat of steel production, they pour all of this raw material into this vat. They heat the vat to very high temperatures. They they remove the impurities. Then they roll the steel out. That's a high-level overview of how you create steel. As they're rolling the steel out of the mill, they have these electronic eyes that every 12 inches or so take a look at the steel. They look at such things as the temperature, such things as the width of the steel, such things as the rate that it's being produced. There's all kinds of factors that engineers use to create the measurement of the output and product of a steel mill. And so what you find is with machine-generated information, like an electric eye, you end up generating huge amounts of data. And so here we see that we have different measurements of data. We have different temperatures and other measurements of data. Time, temperature, and width of the steel would be three of the things that we would look at. So there's a third form of data out there in the world. There's machine-generated. By the way, machine-generated data is oftentimes called analog data or IoT, Internet of Things data. So if you see these terms out there, that's what we're talking about. So what we find is with machine-generated data, much of the data is repetitive. So when we find to do the analysis on machine-generated data, typically 99% of machine-generated data is uninteresting, that there's really not anything that's normal or abnormal about the data. However, every now and then, we find a measurement of the data that is not normal. We find something that a measurement is out of tolerance. And then the machine-generated data goes from being very uninteresting to being very interesting data. And so this is the nature of machine-generated data. Number one, to have a lot of the machine-generated data. Number two, to have only a fraction of the machine-generated data being interesting. But when the data becomes interesting, it becomes really interesting because it's a factor in the determination of the quality of the product that we're producing. And any manufacturer will tell you that the quality of the product they're producing is something that you need to improve. So let's take some examples of machine-generated data. In case it's not interesting, obvious what we're talking about here, let's take a surveillance camera. You go to Walmart, you go to your grocery store, you go to work or wherever you go, and in your parking lot is a surveillance camera. Now, and what is that surveillance camera doing? Every typically 1/30th of a second, a snapshot is taken of whatever the surveillance camera is looking at. And so that's what we see. Now, what does a surveillance camera see? We find out that 99.99% of what the surveillance camera sees is very ordinary, very normal, and not of much use. Because what does the surveillance camera see? They see a parking lot. They see a few cars coming, a few cars going, people getting into cars, but that's not very exciting. However, every now and then, once in a blue moon, They see somebody trying to break into a car, or they see somebody having an accident. And the images taken by a surveillance camera during these circumstances are very interesting. So this is another way of thinking of machine-generated data, is that a lot of data is generated and only a small fraction is interesting. But when I say it's interesting, that small fraction that's interesting is really interesting. It has great business value to the world that we're living in and we create today. Another example of this is a rocket launch. Now, I have to tell you, when I started my career many years ago, I'm not going to tell you how many years ago, but most of you, I dare say, were not even born when I started my career. But I started at a place called White Sands Missile Range in New Mexico. And I was a midnight operator while I was going to school there. And I worked out at White Sands, and we had these big computers that gathered information. Now, what information did they gather? They gathered information about rocket shoots. And once or twice a week, they would shoot a missile from Green River, Utah, down to the White Sands Missile Range. And what would these machines do? These machines would take what's called telemetry information from the rocket. As the rocket was fired, it started generating electronic information very, very quickly. And the kind of information that was generated by the telemetry was such things as, what is the altitude of the rocket? What is the speed of the rocket? What is the direction of the rocket? How much remaining fuel did we have? And so this is what the scientists needed in order to improve the rocketry that we had. And this is what goes on in a machine-generated information gathering for a rocket shoot. Now, the scientists gathered a huge amount of information, but again, 99.99% of the data that was gathered by the scientists wasn't of much use or interested. However, the 0.001% that was generated was very useful for the scientists to understand the value of the rocket shoot. Now, while we're on the subject, I have a quick little humorous. I'm glad this is humorous, but this is a true story. I don't think this ever got out in the papers, but I know this to be a fact. They used to shoot the missiles from a place called Green River, Utah, into White Sands Missile Range in Mexico. Well, if you were to look on a map and to take a ruler, you would find out that not far from White Sands Missile Range was the country of Mexico. And one day, one of the missiles didn't operate properly, and the United States shot a missile into Mexico. And under other circumstances, that would be an act of war. I mean, that would be a big deal. But the Mexicans, to their credit, they found the missile, and then they put a big tape around it, and they charged people like 3 pesos a piece to go in and look at the missile. They turned it into a tourist attraction in Mexico, rather than to think the United States had gone to war with Mexico, which of course we didn't do at all. Anyway, that's a true story, by the way. And I think it was covered up very nicely and well by the people, and the people in Mexico never ever thought we were trying to shoot missiles at them. It was simply a malfunctioning missile coming from Green River, Utah. Anyway, I thought you might enjoy that little anecdote from the past. So today we find that there's 3 kinds of data in the world: structured data, textual data, and analog IoT data. And there are people that are out there that say, gee, we have this kind of data, let's put them into something called a data lake. And you can read about data lakes from lots of places and lots of people get excited and talk about data lake. And the idea is that we simply will take the data from any of these worlds, put them into the data lake, and we will use the data lake for the purposes of analytical processing. At least that's the theory. What we find out rather quickly is that the data lake turns into something more akin to a swamp of data. And why does the data lake turn into, pardon me, a swamp? The data lake turns into a swamp because nobody can use the data. They put the data in the data lake, but then going back into the data lake, trying to do analytical processing from the data lake is something that is, I'm not going to say impossible, but very, very difficult to do. And people don't do well with things that are very, very difficult to do. That's just human nature, and that's just human nature. So what we found is that we have this thing called the data lake, turns into a data swamp. And what's the problem? Nobody can find anything. Nobody can relate data together. It's a big mess. And that's what the data lake turns into. So in terms of our rendition of architecture, we find out that in order to make our data lake useful, we've got to create something called an analytical infrastructure over the data lake. And this, by the way, is something called a data lakehouse. Now, this analytical infrastructure is something that is not particularly easy to build because there's a lot of components. We're not just putting structured data in there, we're putting all kinds of data in there. The kinds of things we need in the analytical infrastructure for our data lakehouse include such things, and this is not an exclusive list. There's other things that haven't even made this list, but such things as metadata. What do our attributes look like? What do our keys look like? What do our indexes look like? Definitions. What is data defined to be? What do we have in there? Taxonomies. We need taxonomies because we put textual data in there. Ontologies. Ontologies are simply a more sophisticated form of taxonomies, but ontologies help us understand the textual information that's in there. Another thing we need to put in there, it's very important, the inclusion and exclusion criteria. Why was data included from one place? Why was it excluded? And the inclusion exclusion criteria is very important. Data lineage. We need to talk about where the data comes from, how it got there, what it's gone through in order to understand how to use it. Mapping. There's some interesting stuff called mapping that's got to be done to show us how the transformation is done. Summarization algorithms, that some of the data in our data lake is summarized data. How did it get to be summarized? What logic was used? And this is just the tip of the iceberg for what's required for the analytical infrastructure. But without the analytical infrastructure, we've got a swamp. With the analytical infrastructure, we now have the chance of going into our data lake and turning our data lake into something that is useful. So when we put this analytical infrastructure over the data lake, that then becomes the data lakehouse. And in terms of what people are talking about and what they're saying, this is what is what's being discussed. So we find then that when we create our data lakehouse, all kinds of data go into the data lakehouse. Applications data, data warehouse data, textual data, machine generated data, all of this belongs in our data lakehouse environment. And that's how the evolution to the data lakehouse has occurred. One of the things about machine generated data is that, or one of the challenges of the data lakehouse is that machine generated data is very, very structurally different than data warehouse data or structured data. Data warehouse data is typically in the form of a common structured format. Machine generated data is anything but the structured format that we're used to. So one of the challenges of the data lakehouse is being able to marry these kinds of data together. So that then are the challenges of the data lakehouse, taking all of the different kinds of data, bringing them together into a concert. I kind of liken this to a symphony symphony orchestra. You've got violins in one section, cellos in another section, French horns in another section, drums in another section, piano in another section. And in order to make all of this, make beautiful music, you need to have a conductor that knows when it's appropriate for one instrument to play and when it's appropriate for another instrument to play. And that's the kind of orchestration that you need for being successful in the data lakehouse environment. So that then is the my presentation to you. We have time for questions. I'm happy to take questions.
Bill, I imagine you could not hear the question, or could you hear the question?
That's correct. I can hear you, but I can't hear the person.
So the question was what are some examples from a tooling or technology or provider's perspective of being able to implement a data lakehouse, like for example, Databricks and other providers?
I don't want to sound like a salesman, because I'm not. But in terms of the infrastructure capabilities, Databricks and Forest Rim technology have, Databricks does really well with the machine generated data. Forest Rim does really well with the textually generated data. So those would be the two vendors that I would look at.
What role does the data lakehouse architecture play in the democratization of data in terms of things like security, access, domain-specific data, things like that?
The data lakehouse plays the role of orchestrating the different kinds of data into a position of doing analytical processing. If what you mean by democratization of data, you mean the ability to do analytical processing, then you very much need the architecture of a data lakehouse. Now, if you don't care about doing analytical processing, if you don't care about the integrity of the data that you've got, then you don't need a data lakehouse. But then you also probably will be looking for a job as well.
How do you move people that are in the more traditional cloud data warehousing environment to a data lakehouse as we're discussing it today?
I'm going to unfortunately show my prejudice, but I'm going to at least be honest about this and tell you that I'm prejudiced before I answer the question. So here goes a prejudiced answer. Putting a data warehouse in the cloud is nothing. That if you have a big mess on your hands and you put your big mess in the cloud doesn't do anything for you to make the mess get cleaned up. So if you put a big mess into the cloud, what do you end up with? A big mess on the cloud. And so I think that putting things onto the cloud is just another silver bullet that our profession has been famous for. People thinking, I work with one organization and they think, oh, all we have to do is put things on the cloud. And I asked them, what do you think is going to happen when you put this on the cloud? What magic do you think is going to happen? There's no magic that's going to happen. You've got the same data, the same issues of the inability to analyze the data, the inability to take the data and group it together and put it into a form that can be analyzed. What do you and nobody has an answer to that. Oh, we put it in the cloud and something magical happens. Well, I got news for you. You can put anything you want in the cloud, but nothing magical is going to happen. So now I'm prejudiced about that because in our industry today, it's fashionable to say, "Oh, we put it in the cloud," and I go, "Okay, that sounds good." You still got the same problems you always had when you put something on the cloud. Nothing magical happens when you put it on the cloud.
Any recommendations in terms of best practices for managing things like capacity, storage, compute, cost for data lakehouse?
The single most important factor in managing cost, managing storage, and putting things are the managers and the sophistication of the managers of the process. It's not the technology, it's the people and the usage of the technology that make all the difference. So get somebody that knows what they're doing architecturally, and you're gonna, that's where you should be putting your money. People don't like to hear that, by the way. That's not a popular thing to say, but because people don't like to be told that you've got to be smart, you've got to roll up your sleeves and do work when it comes time to do that. And people don't like being smart and rolling up their sleeves. They think that there's some silver bullet out there that's going to come along and save the day. Our industry's been looking for the silver bullet longer than most anybody in this room was even living. We've been looking for the silver bullet, and I have news for you. There is no silver bullet, and trying to find that magical piece of technology that's going to make everything right is not going to happen, not in our lifetime.
In terms of that orchestration, who's going to be the conductor that brings all that together?
It's kind of interesting. It's going to be a combination of skills. It's going to be the data scientist and the data architect. The problem with that equation is the data scientists don't think they need the data architect. Let me tell you what it's like. It's like going in for an open heart surgery. When you go in, or let's forget open heart surgery. You go into the hospital and you need to have an operation on some part of your body. I don't know what, I don't care. What do you get? You get a surgeon and you get an anesthesiologist. In every case, the surgeon won't perform the operation unless there's an anesthesiologist there. Why? Because during the operation, while you're under the anesthesia, you need somebody concentrating on the work that needs to be done and somebody concentrating on keeping you alive, because it's entirely possible that the surgeon can do the best job possible and you die while you're on the table. So the orchestration is a combination of data science and data architecture. The problem is the data scientists, God love them, I got a lot of little friends of mine, but the data scientists have been conditioned to think that all there is to doing what they're doing is the data science part. They don't recognize that they need that anesthesiologist there keeping the patient alive while the operation is going on. So the orchestration is going to be a combination. Now the data scientists are not dumb people. They may have been miseducated, but they're not dumb. And very quickly they realize that they need help with data architecture. So the orchestration is going to be done by a combination of the data scientist and the data architect working side by side to make sure the operation is a success.
All right, we're at time. Let's give Bill a round of applause. Thank you very much, Bill.
Thank you. Sorry I couldn't be there today in person.
Thank you, Bill. Really appreciate you stepping up and doing this despite the circumstances. I'll end the meeting now, and I'll give you access to the recording if you want.